Hello, ma'am. My name. Today I'm going to explain about time frequency analysis of harmonic oscillator motion. Introduction of simple harmonic motion. The harmonic oscillator is undoubtedly the most widely studied mechanical system, both in classical and quantum mechanics. There are a number of reasons for this. Firstly, the simplest vibratory motion is in nature. Secondly, the most importantly, for almost all forces when a system is in equilibrium and disturbed. From that position, when then to a high degree of approximation, the resulting motion is harmonic. Third, chains of harmonic oscillators have been used to study multidimensional systems. Fourth, studies of equilibrium and evolution of n bodies can be rapidly tested on chains of harmonic oscillators. Fifth, the equations governing electric circuits follow, follow the harmonic oscillator equations. Finally, the harmonic oscillator is exactly solved. While many methods have been developed to study the harmonic oscillator, no one to the best of our knowledge has studied it using time frequency methods. It is the purpose of this paper to do so. We know now discuss for what type of problems and solutions will time frequency methods are effective. Work supported by the NASA JOV program, Office of Novel Research and the programs. Be able to understand how frequencies change in time and therefore the methods are ideally suited to study transient phenomena and more generally situations that are non-stationary. We now give some simple examples where we think time frequency methods will be affected. Because of that, the main equation shown below is shaped like a sine curve. It says that the displacement is equal to amplitude of the variation A, otherwise known as the maximum displacement multiplied by sine omega t, where omega is the angular frequency of the variation and t is the time. This displacement can be in the x direction or the y direction, depending on the situation. A vertical mass on a spring varies in the y direction. Sinusoidally, a horizontal mass on a spring varies in the x direction. Sinusoidally, a pendulum has a such variation in both directions. Here, t equals to 2 pi under root m by k. M is the mass of object in kilograms. K is the spring constant of spring. T is the time period of oscillations. This equation has a sign in it and a sine graph starts at 0. Using this equation is like starting your mathematically stopwatch in the middle of a pendulum spring. T equals to 0. This is the center of the oscillation. If no the other hand, on the other hand, you replace a sine with a cosine, then the equation is still correct. You are just starting to measure time at the maximum displacement instead. But we also need to define the angular frequency. Angular frequency is the number of radians of the oscillation that are completed each second. A full 360 degrees is 2 pi, 2 pi radians, and that represents one complete oscillation from the middle to a fully stretched spring, back to the middle to a fully compressed spring, and then back to the middle again. You can convert angular frequency to by dividing by it by 2 pi. Angular frequency F just tells you the number of full cycles per second measured in hertz. It also worth nothing that time period t, such as was used in the first equation, is equal to 1 divided by the frequency f. So because of that connection, you can get a question that crosses over between all three of these equations. X equals to a sine omega t. T equals to time in seconds. Omega is equals to angular frequency in radians per second. A equals to amplitude in meters. T is displacement is in meters. Numerical methods. While the harmonic oscillator with a sinusoidal driving force can be solved exactly, it can not be solved exactly for almost any other external force. Therefore, we have restored to numerical integration. We now describe the methods we have used for a single harmonic oscillator with mass m, spring constant k, damping constant b, and time dependent external force f of t. The equation of motion is. We have used two ways to integrate the equation of motion. First is by using a standard routine for numerically solving differential equations. For example, by the Range-Kutta method. Secondly, for the harmonic oscillator, the Green's functions can be explicitly obtained, and therefore a general force the solution can be written down as an integral of the Green's function with the force. We have used both methods and we discuss below the issue of accuracy. One common way to ascertain the accuracy of integration is to use an integral of the motion. For example, the energy, and see how constant it remains during the evolution. In our case, we do not have a constant energy situation, but even if we did the energy criteria is not very sensitive. A better means of ascertaining accuracy is to evolve the system up to a time t, and then reverse the velocities and evolve it again for a time t. This is microscopic reversibility, which occurs that the system returns to the initial starting point. This is a very stringent test, although not foolproof. Our tests show that indeed our integrations are very accurate. For example, when we evolved a system for about 200 resonant accuracy cycles and reversed it for another 200 cycles, the difference in the initial and final positions. Derivation. F equals to minus kx equals to ma. X equals to minus k by m into x equals to minus omega square x, where omega equals to under root k by m. If x not equals to 0, then x equals to a sine omega t. V equals to dx by dt equals to omega a cos omega t. A equals to dv by dt equals to d square x by dt square equals to minus omega square a sine omega t equals to minus omega square x equals to minus k by m x, k by m into x. If x not a, if x not equals to a, then x equals to a cos omega t. B equals to dx by dt equals to minus omega sine into omega t. A equals to dv by dt equals to dx square by dt square. D square x by dt square equals to minus omega square a cos into omega t equals to minus omega square x equals to minus k by m into x. In general, x equals to a sine into omega t plus pi. V equals to dx by dt equals to omega a cos into omega t plus pi. A equals to dv by dt equals to d square x by dt square equals to minus omega square sine a minus omega square a sine into omega t plus pi equals to minus omega square x equals to minus k by m into x. Examples. We now discuss some examples of cases we have integrated and examined in the time frequency plan. Since the main purpose of this paper is to show that time accuracy methods are effective, the plots we show are the dimensionless units. However, for each example, we give the number of resonant cycles that the oscillator went through in the time indicated in the graph. The time frequency plots we are in the dB scale unless otherwise noted. We drive a single non-damped oscillator with a trip force, in which case the equation of motion is where W0 is the starting frequency. Note that the instantaneous frequency of the driving force is the derivation of the phase. Wi equals to W0 plus Pt. In the indicated by the time axis of elapsed time was about 70 cycles during the transient period. The natural frequency and trip frequency coexist in equal magnitude, although the spring starts from test, the trip immediately excites it to its resonant frequency until the driving force hits the resonant frequency. The oscillations are such that it is multi-component, that is, the spring is oscillating with two frequencies, his own natural frequency and that of the driving force. When the trip frequency becomes very close to the natural frequency, the oscillator starts to resonate with increasing amplitude. From this point on, the natural frequency of the spring dominates the strip frequency, and eventually the strip frequency dies out. The oscillator behaves as if it is undergoes a free oscillation, even though there is a continuous driving force applied to it. We consider now the same case, but we change the magnitude of the strip by a factor of 1000. It turns out that the behavior it is the same as in the case above, except that everything seems to be scaled. We increased the natural frequency by a factor of 100, keeping other fluids the same. The resultant behavior was the same, except that the transient period was increased by factor of 100. In one of the cases we observed an interesting effect that has been previously observed for a number of signals. This is illustrated with in which are respectively the spectrogram and jam distribution. The effect is what has been called an islet. It seems that a line splits into two. The origin of this effect has been previously investigated, and it appears to show up when there is a discontinuity in the phase. Whether that is the case here, we do not know and are currently investigating it. We now consider a spring driven by the sum of two strips and where the spring has a damping force. The equation of motion is the number of elapsed cycle is about 840. When the frequency hits the resonance frequency, the oscillator is excited, but the oscillations die down until the second strip crosses the resonant frequency. The time frequency plot clearly shows these effects, while if one were to look at the time series, nothing clearly could be seen. The total number of elapsed cycles is about 2000. We observed similar effects as with the cases previously discussed. The time frequency plot shows effectively the quadratic frequency of the driving force. Conclusion. The above classes are shown that the time frequency methods illustrate very clearly what happens to the oscillator, and in particular it shows very clearly the transitions from one frequency to another. It would be very difficult to see these transition by other methods. Certainly standard Fourier analysis would not show them, as it would simply give the spectrum for the total time duration. In addition, the plots illustrate in a clear way when the signals are multi-component. Thank you, ma'am.